My name is Rishabh and I'm from CSE AML branch second semester. I'm going to talk about the basic electrical and electronics engineering subject which have a topic what is the principle of operation of a single phase transformers and which law governs its function. In this slide we are going to learn about what is a transformer and why does it exist. A transformer is a static electrical device meaning it has no moving parts that transfers electrical energy from one circuit to another through the principle of electromagnetic induction, while simultaneously changing the voltage and current levels. The word static is important. Unlike motors or generators, the transformers have no rotating components, which makes them extraordinarily reliable and efficient. The fundamental reason transformers exist is a practical engineering necessity. Electrical power is more efficiently transmitted at very high voltage to minimize current and therefore resistive losses in transmission lines, but it must be used at much lower voltage for safety in homes and industries. Without transformers, you would either waste enormous amount of energy in transmission or you would need to generate electricity right next to where it is used. Transformers solve this by stepping voltage up at a generating end and stepping it back down at the consumption end, making the entire modern power grid possible. In this slide, we are going to learn one of the main law, the governing law of the transformers, known as Faraday law of electromagnetic induction. The entire operation of the transformers is governed by Faraday law of electromagnetic induction, formulated by Michael Faraday in 1831. The law states that the electromotive force EMF induced in a conductor is directly proportional to the rate of change of magnetic flux linkage through that conductor. Mathematically, it is E is equal to minus n d phi by dt, where E is induced EMF in volts, n is the number of turns in the coil, phi is the magnetic flux in the Webers, and t is the time. The negative sign comes from the Lenz's law. The induced EMF always opposes the change in flux that caused it. This is the consequence of the conversion of energy. The induced current must resist the change, otherwise you would get energy for free. Without a changing magnetic flux, there is no induced EMF, which is exactly why transformers only work with alternating current AC, not direct current DC. DC produce a constant flux and a constant flux produce zero induced EMF. In this slide, we are going to learn about Lenz's law and its role in transformer behavior. Lenz's law is so important to transformer operation that it deserves its own slide. It states the direction of an induced current is always such that it opposes the change in magnetic flux that produces it. In a transformer, when a primary coil carries an increasing current and magnetic flux through the coil increases. By Lenz's law, the current induced in a secondary coil will flow in a direction that creates a magnetic field opposing this increase. This opposition is not a flaw. It is the physical mechanism by which energy is transferred. The secondary opposing flux forces the primary to draw more current from the supply to maintain the original flux level, which is exactly how power gets pulled through. The transformer from primary to secondary when a load is connected, remove the load and the secondary draws no current. And indeed, the primary draws almost no current either, just a tiny magnetizing current, which is why unloaded transformer consume very little power. In this slide, we are going to learn about the physical construction of a single phase transformer. A single phase transformer has three essential physical components. The primary winding is a coil of insulated copper wire connected to the input, which is source voltage. The secondary winding is a separate coil of insulated copper wire connected to the output, which is load. The magnetic core, typically made up of a thin laminated sheets of silicon steel, provides a low reluctance path for a magnetic flux to flow between the two windings. The two windings are electrically isolated from each other. They share no direct electrical connection. The only link between them is a magnetic flux through the coil. The laminated construction of the coil is deliberated. Solid iron cores would have large eddy currents, circulating currents induced in the iron itself by changing flux, which waste energy has heat. Thin lamination installation from each other dramatically reduces eddy current paths and therefore eddy current losses. Silicon steel is used because it has high magnetic permeability and low hysteresis loss. In this slide, we are going to learn step by step how a transformer actually works. Let's walk through the operation from start to finish. Step 1. An AC voltage V1 is applied to the primary winding. which has N1 turns. Step 2. This alternating voltage drives an alternating current through the primary winding. Step 3. The alternating current in the primary creates an alternating magnetic flux phi in an iron core, oscillating at the same frequency as the supply, 50 Hz or 60 Hz. Step 4. This alternating flux passes through the magnetic core and links with the secondary winding, which has N2 turns. Step 5. By a Faraday law, the changing flux induces an EMF in a secondary winding. E2 is equal to N2 into d phi by dt. Step 6. If a load is connected across a secondary, this induced EMF drives a current through the load. Step 7. The power drawn by the load is supplied minus losses from a primary source. The entire energy transfer happens through a magnetic field. No direct electric connection between primary and secondary circuits is involved at any point. In this slide, we are going to learn about the EMF equation of a transformer. The EMF equation is one of the most important analytical results in transformer theory. For sinusoidal varying flux, phi is equal to phi m is into sine 2 pi ft, where phi m is the maximum flux and f is the frequency. Faraday law gives instantaneous induced EMF as E is equal to n into phi m bracket open 2 phi into f cos 2 phi into f into t. The RMS value of this induced EMF, which is what we actually measure with a voltmeter, works out to be E is equal to 4.4 into f into n into phi m. The constant 4.44 comes from 2 pi by root 2, which is equivalent to 4.443. This equation applies to both windings. E1 is equal to 4.44 f into n1 into phi m for the primary, and E2 is equal to 4.44 into f into n2 into phi m for secondary. Since both the windings shares the same core flux phi m, dividing this equation gives E1 by E2 is equal to n1 by n2. This is the turns ratio, the fundamental relationship that determines how much the voltage is stepped up or down. The EMF equation also tells you that for a given supply frequency and core, the maximum flux is fixed by a primary voltage is a crucial design constraint. In this slide, we are going to learn about the turns ratio and voltage transformation. The turns ratio, also called as transformation ratios, is defined as a N1 by N2 is equal to E1 by E2, which is approximately V1 by V2. The approximation holds because winding resistance drops are usually small compared to the voltage. This single ratio governs the entire voltage transformation behavior. If N1 is greater than N2, more turns on primary. Then V1 is greater than V2, the transformer step down voltage. If N2 is greater than N1 and then V2 is greater than V1, the transformer step up voltage. If N1 is equal to N2, the transformer is a 1:1 isolating transformer. Voltage are same, but the two circuits are electrically isolated, which is valuable for safety. A transformer at a power substation might have a turns ratio of 4 lakhs is to 11,000, stepping 400 kilowatts transmission voltage down to 11 kilowatts for distribution. A small adapter charger might have a ratio of 230 is to 12 to a power a device. The turns ratio is the simplest and the most powerful design parameter in a transformer engineering. In this slide, we are going to learn about the current transformation and conservation of power. A transformer not only transforms voltage, it simultaneously transforms current in the reverse ratio by the conservation of energy in an ideal transformer with no loss. V1 I1 is equal to V2 I2, meaning input power equals output power. Combining this with V1 by V2 is equal to N1 by N2 gives I1 by I2 is equal to N2 by N1 is equal to 1 by A. So if a transformer steps voltage up by a factor of 10, it steps current down by a factor of 10. The VA volt ampere product stays constant. This is why a high voltage transmission line carry a low current. A transformer step up voltage and step down current, dramatically reducing I square R losses in the transmission wire. This is inverse relationship between voltage and current in transformer is a direct consequence of energy conservation combined with the turns ratio, and it's one of the most elegant results in electrical engineering, a lossless device that can trade volts for amps at will. In this slide, we are going to learn about the ideal transformer, assumption and model. To develop a clean analytical understanding, engineers first study the ideal transformer, a mathematical abstraction with four key assumptions. First, the winding resistance are zero, no copper loss. Second, all flux is confined to the core and links both windings completely. There is no leakage flux escaping into a surrounding air. Third, a core has infinite permeability. It takes zero magnetizing current to establish the flux. Fourth, there are no core losses, no hysteresis loss and no eddy current loss. Under their assumption, V1 by V2 is equal to N1 by N2 is equal to I2 by I1 exactly. The ideal transformers is a useful starting point for a circuit analysis and reveals the fundamental relationships without the complexity of a real losses. All real transformer analysis builds on an ideal model by adding correctness terms. Resistance, leakage, reactance, magnetizing branch to account for the physical imperfections of a real material and real windings. In this slide, we are going to learn about the transformer losses, copper loss and coal loss. Real transformers are not 100% efficient. Energy is lost in two main ways. Copper losses, also called as I square R losses or winding losses, occurs because of the windings have finite resistance. Power dissipated is equal to I1 square R1 plus I2 square R2. Copper losses are variable. They depend on the square of the current, so they increase significantly with load. Core losses, also called as iron losses, occurs in magnetic core and have two components. Hysteresis loss arises because of the magnetic domain in the iron must realign every half cycle of alternating flux. This domain reversal dissipates energy proportional to the area of BH loop and thus proportional to the frequency and the 1.6th power of the maximum flux density. Eddy current loss arises from the current induced in the core itself by changing flux. P is equal to Ke into F square Bm square into T square, where T is lamination thickness. Core losses are essential constant regardless of load. They depend only on the supply voltage and frequency, which are nearly fixed in operation. Conclusion: a single-phase transformer is a static device with no moving parts that transfers electrical energy between two isolated circuits purely through electromagnetic induction. Its entirely operation is governed by Faraday law, E is equal to minus N into d phi by dt. At the turns of ratios N1 by N2 controls voltage and current transformation. The EMF equation E is equal to 4.44 into F into N into phi m connects frequency, turns and flex to induce voltage, and real transformers loses energy through copper losses, variable, load dependent and core losses, constant and voltage dependent. Despite these losses, modern transformers achieve efficiency above 98%, making them the backbone of every power grid on the planet. Without transformers, long-distance power transmission simply would not exist. Thank you.